Welcome back. Today we have the integral of x squared times sine of ln of x dx. So when we stumble across the integral for the first time, we are very overwhelmed. There are a lot of thoughts flooding in as to all the different techniques we know of that we can solve the integral with. But definitely one of the first thoughts that should come to mind is, can we do a u sub? Now for this one, it's not straightforward that we can pull off a u sub, but we can. And the idea is the intuition is that whenever you see a composition of functions, in this case we have the ln of x making up the argument of our sine of x, we should ask ourselves, will it simplify the problem if I set the argument equal to u? Does it help us? So let's see what happens. If we set u equal to ln of x, well, if we differentiate both sides with respect to x, right, we end up getting a du equals 1 over x dx. And when we substitute back in, we get that the dx gives us a factor of x du, making this an x cubed. Sine of u du did absolutely nothing. So what gives? The trick is, not only should we ask ourselves, does it help us to set the argument equal to u? Every time we have u equal to the natural logarithm or a logarithm, we should also be asking ourselves, does exponentiating both sides benefit us? So it does. If we exponentiate both sides, we end up getting that e to the u gets us e to the u equals x. And well, differentiating both sides, we get e to the u du equals dx. And we can clearly see that now we can plug in back for x, and we get the integral of an exponential in terms of u times the sine in terms of u, and then the extra factor of that exponential. It works out. We end up getting the integral of e to the u sine u of dx. Well, not e to the u. It's going to be a little more involved than that, but we can perform integration by parts, and it did end up simplifying the problem. So let's see what this yields us. We end up getting the integral of e to the u squared, which is just e to the 2u, e to the 2u times sine of u, and then e to the u du. This e to the u merges in with this one, and we end up getting this turning into a e to the 3u. And there we go. We can now perform integration by parts, where the di method, we're going to set the differentiation column to e to the 3u, e to the 3u, and then sine and u in the integration column, and integrating, we get that this is the cosine of u, negative cosine of u. And then the integral of negative cosine of u is negative sine of mu. Here we get differentiating, we get a 3 e to the 3u, and then we get a 9 e to the 3u. Don't forget our plus, minus, plus. We multiply these two, and then multiply the integral of these two. And we end up getting the solution is, if this is our integral I, we end up getting that e to the 3u minus e to the 3u cosine of u plus 3 to the eu e to the 3u sine of u minus, notice we get a minus the integral of 9 e to the 3u sine of u, which is our original I. So we could write minus 9i and we get that this was all equal to I, right? Running out of space there. So we can add 9 on both sides, which gives us a 10i on the left, and dividing by 10 on both sides, we get that the integral equals all of this junk divided by 10. Don't put in your plus c, and or do, up to you. And so we end up getting minus e to the 3u. Well, e to the u is x, so e to the 3u is x cubed. So e to the, so this becomes a minus x cubed cosine of u is ln of x plus 3 e to the 3u is again x cubed. We have a sine of u, which is a sine of ln of x, all divided by 10. And now we're done.